It looks like a lot of people who watch my channel are interested in game development, optimization, and high-performance programming. So I wanted to make a video on how to write fast code using features that low-level languages like C and C++ provide. These topics also show up in interviews for coding jobs where performance is important, such as game development and scientific computing, so they're good to know in general. At the end of the video, we'll test everything to see how much of a speed up we get. I think the results might surprise you. To see how this all works, let's think about this code to represent a circle. In C or C++, we can do this with a simple struct that stores a position, xy, and a radius r. Believe it or not, circles are everywhere in game programming, but they're often hidden. Consider this royalty-free, non-trademark video game hero. If we have something flying at our hero, like maybe an arrow, it's typically too slow to do a pixel-by-pixel analysis of collision. So we're going to approximate everything on our screen with a simple shape, like a circle. Now, testing if you've been hit becomes as simple as testing if the two circles are overlapping. If you've never written circle-circle intersection code before, it looks something like this. The first step is to find the distance between the centers of the two circles, which is the square root of the x distance squared plus y distance squared. Then, we'll find the sum of the two circle radii. If the distance between the circles is greater than the combined radius, we know that the circles are not overlapping and there's no collision. But if the circles are closer and the distance is less than the combined radii, our circles are overlapping and we have a collision. Remember, these circles represent entities in our game. So when the circles overlap, we know that our hero, has been hit and should lose a life. Actually, I would personally never write code like this. The square root is slow to process on almost any hardware, and working with floating point numbers can be much slower than sticking with integers. We can solve both problems by just getting rid of the square root. Then instead of comparing distances, we can compare squared distances. So if the squared distance between the circles is less than the combined squared radius, we know we have a collision. I timed it on my computer. The square root takes about 2.5 nanoseconds. That's 2.5 billionths of a second, which I know sounds fast, but all of the other lines in our collision code together take 3 nanoseconds. So when we're worried about shaving off 2.5 nanoseconds, we're actually worried about doubling the speed of our circle-circle intersection time. And often we have many, many circles to consider. Each character in the game needs their own collision circle. Assuming your players or characters can interact with anything, each thing they can interact with needs a circle. And man, if you want highly destructible environment, then anything that you can destroy needs a circle. Avoiding square roots is good, but it's just the tip of the iceberg. And there's an important optimization secret I want to share with you. The secret to optimization is that your computer's processor is insanely fast, shockingly fast. Your CPU can compute 1 billion operations every second. So what makes code slow? It's memory. Your processor is an absolute speed demon, but it can only work on whatever data is sitting in its registers, specialized fast storage connected directly to the core compute logic. And modern processors only have between a few dozen and a couple hundred registers, depending on the exact chip. Data gets to the registers from the L1 and the L2 cache, where your processor stores data that it thinks it might need. But each of these caches only hold a few megabytes. So your computer has RAM chips to store all the data your program's actively using. RAM can be expensive, but if you're willing to pay, you can typically get several gigs of RAM. Data not being used will be left on your hard drive or other storage, which is basically unlimited for most practical purposes. What's the problem? A circle's only a few bytes, and we have gigs and gigs of storage. Why am I worried? Well, the problem is that all the big storage is slow. Getting data from even a fast hard drive is going to take several milliseconds. And by that time, our character's already moved a few pixels past the point where you're checking, so everything ends up feeling laggy. RAM is much faster. Getting data from RAM only takes something like 10 to 20 nanoseconds, but your processor's even faster. It only takes 1 nanosecond or so to pull something out of cache. And it's down to something like 1/4 of a nanosecond to do a simple computation if the data is already in the registers. So if you could somehow magically keep all your data in the processor's cache and registers instead of RAM, everything could run 15 to 50 times faster. Okay, that's the theory. In reality, the situation is always much more complex, and seeing a 15x speedup is unlikely. But when you're dealing with large amounts of data, being thoughtful about how it's stored is always important, and in my experience, your code will get measurably faster. Memory-aware programming can be even more important when developing for consoles or embedded systems where you might have a very strict memory hierarchy that's rigid about what you can do. So that's the secret to fast code, keeping everything in cache. Cache-aware programming strategies are a big topic, but for now, I just want to show you one way to save in memory, which is to pack your data structures into less space. Here's our simple circle class from before. We can use the size of command to see that it takes up 12 bytes of memory. That makes sense. We have 3 integers, each of which are 32 bits or 4 bytes, and 3 times 4 is 12 bytes. How could we possibly do better? Well, if we know something about the size of our screen the character's on, we can actually optimize this structure. Let's say the display is 1024 pixels wide by 768 pixels tall. Then we know our circle's x value will always be one of the 1024 values between 0 and 1023. Assuming we restrict our radius and y position to be in the same range, how can we exploit this? Well, log base 2 of 1024 is 10, which means 2 to the 10 is 1024. That means with 10 binary bits, we can represent 1024 different values, starting with 0000, 0001, 0010, and all the way up to 11111, which we'll interpret as the values 0, 1, 2, and 3, all the way to 1023. That means we can represent anything we care about in terms of pixel addresses with only 10 bits of data. So let's add a constant representing this value 10. And now, in C, C++, we can use this bit field notation with a colon to tell the compiler that each of these variables only needs to be 10 bits long. The compiler will then pack all 3 10-bit variables into a single 32-bit integer. Running size of, again, shows us that our circle struct has shrunk from 12 bytes down to 4. A big win for memory usage. Okay, this was effective, but a little too easy for my tastes. Let me show you how to roll your own bit field so you're in full control. We're going to take everything in our circle structure and replace it with just a single integer. This means we can't initialize the values as easily as before, so let's store each of these initial values in their own integer and initialize our circle data value to 0. Now, to set the x value, we can take the binary OR between the current value of 0 and the target x value we want for the circle. If you've not seen it before, this pipe symbol means an OR in C. Taking the OR of some value in 0 has the effect of replacing the zeros with whatever the new value is. Our circle data is a 32-bit integer, and we know this x value is only 10 bits. So that means we have 22 bits left over in the data to store our y value. If we use the shift operator to move the y value 10 bits to the left, and then OR the result with the current data, we know we won't conflict with the x values because those are written to the first 10 bits. With the x and y values packed in, we're still only taking up 20 bits. That leaves 12 bits left over for the radius. Like before, we need to shift the radius value, this time 20 bits, so as not to conflict with either the x or the y value that we've already written. Okay, I don't think that code's too bad. What about reading the values? Well, if we define a mask of a bunch of zeros followed by 10 ones, we can take the binary AND between this mask and the structure data integer to recover the x value. Because the binary AND will discard anything where there's a 0 in the mask, we're left with only the final 10 bits, which is where we stored the circle's x value. To get the y value, we can shift the data 10 bits to the right, and then AND that with the same mask. And to get the radius, we shift 20 bits to the right and AND with the mask again. We don't actually need to apply this last mask, as we've shifted away all the other data, so we can just use the resulting value directly. This ends up leaving 12 bits of accuracy for the radius. Let me know in the comments below if you can figure out why I wanted the extra bits to be in the radius as opposed to x or y. I think the resulting code's not too bad, but if you find it a little too verbose, you can remove the struct and just store all the circle information directly as a single integer. Here's how I might rewrite the same demo using just a couple of lines. Believe it or not, the style gets easy to read once you've gotten used to it. Let's compare speeds. Our first test is initializing thousands of circles. With the standard structure, initializing all the circles takes 70 microseconds. Just switching to a bit field with its smaller memory footprint drops the runtime down to 50 microseconds. And this shocked me. If we switch to our raw int version, the runtime drops again down to 38 microseconds. To me, I found this really surprising. We have to perform several extra ands and shifts, but even with all that extra computation, the bit field is faster because we're using less memory and we're staying more frequently in caches and registers. And extra surprising was that our handwritten version is faster than using the built-in support from the C compiler. I'm not sure what to say. I guess I write fast code. In practice, the biggest speed boost you're going to see is not from working with bit fields or writing optimized code. It's by turning on the optimizations in your compiler. But even using the highest level of optimization, the same trend still stands. Using a bit field is twice as fast as using the standard struct, and our handwritten version with just an integer is faster still. To be extra confident, I averaged the results over several runs, analyzed the uncertainty, and computed a statistical confidence bound. And the improvements in performance we're seeing are statistically significant. Even though there are small variations from run to run, it's faster to use bit fields or integers than it is to use the bloated basic structure. We can also test the speed of using the packed data to do computation. Here, we'll count the number of intersections between circles. With 20,000 circles all sharing a screen, there's going to be a lot of collisions, about 170 million. With the slow square root version of the distance check, it takes almost a second and a half to find all of these collisions. Getting rid of the square root and comparing distances squared drops us to about 0.9 seconds. And moving to an integer gives us a small speed up of 50 more milliseconds. Again, the big win comes from using an optimizing compiler, which leads to an almost 20x speed up in performance. But even here, removing the square root makes the code 2x faster, and packing all the data into a single int gives us another 5% speed up. Even with a good compiler, calling square root makes your intersection code more than twice as slow, which is our first key point for fast code. Avoid square roots and avoid floating points in general if possible. Beyond that, it's important to think about memory and caching, especially if you're working with a memory budget that your compiler might not know about. You can tell the compiler about maximum sizes of values used, either through bit field annotations like we saw at the start, or by getting your hands dirty and manually packing data with low-level operations like bitwise and or, which will give you the best possible performance. These ideas are also important because they show up in places like job interviews, especially in game development. If you're going to be working on performance-critical code, like game engines or game development tools, it's widely expected that you know how to optimize your code for both speed and for memory footprint. If you want to see more about writing optimized code, let me know, and I can follow up with more videos about low-level optimization, cache-friendly programming, and game programming in general. Until then, be sure to check out one of my other videos. I'll see you next time.